Okay, today we're going to learn about rational functions. So this continues on along the same lines of what you learned in Algebra 2. We're going to learn to find the domains of rational functions and how to find horizontal and vertical asymptotes of rational functions. We want to be able to analyze and sketch graphs of rational functions and then also find slant asymptotes. Okay, that may be something that you did not do in Algebra 2, so this last thing would probably be the most complex of the things that we'll tackle today, but this should overall be a review type lesson. So let's talk about domains of rational functions. Rational functions, if you recall, happen when you have a numerator polynomial divided by a denominator polynomial with that denominator polynomial not equal to 0. So anything that is a factor of that denominator polynomial that could make it not equal to 0 is going to be something that we have to consider that it's not in the domain of this overall function. So when we look at this polynomial here, and we have 3x plus 1 on top, on the bottom, when we factor this, what we have is x plus 2 times x plus 1. So that's 3x plus 1 over all of that. Now, things that make the denominator 0, I mean, we can't divide by that, right? So that's not in the domain. So x equal to negative 2 or negative 1 is not in the domain. So my domain is all reals with x not equal to negative 1 or negative 2. Now, horizontal and vertical asymptotes. Vertical asymptotes happen when, okay, remember these are the vertical lines, they're invisible here, when as x approaches a certain number, okay, which is going to be where that vertical line is, the value of my function either goes to positive infinity or negative infinity. So we can see that we've got some of these asymptotes happening in this function right here at positive 2.5 and somewhere around here at negative something or other, right? Okay, well, those are awesome. We also have horizontal asymptotes. Now, actually, let me say one more thing about the vertical asymptotes. The vertical asymptotes, they happen when as x value of a function approaches some number, the function's value itself goes to positive or negative infinity. The number that it approaches is not in the domain, right? So the vertical asymptotes happen at numbers that are not in the domain, okay? Because the number is not in the domain, the values of the functions, it's kind of like slamming up against a brick wall, okay? They can't go there, so they either go to positive infinity or negative infinity, okay? Now, horizontal asymptotes, these, like this one here, just roughly sketching this in, happen when the value of a function approaches a certain number as x either goes to positive or negative infinity. So as x goes to negative infinity here, the value of my function approaches 0. Same with positive infinity. The value of my function still approaches 0. Okay? So this has nothing to do with the domain of the function. It has to do with numbers that the range approaches. So vertical asymptotes happen at the zeros of the denominator function. Okay? And we talked about that in the last slide. Horizontal asymptotes are a little bit different, okay? They depend on the degree of the numerator versus the denominator function. If the degree of my numerator function is less than the degree of my denominator function, then y equals 0, or the x-axis, is a horizontal asymptote. And we saw that happen with my previous function. We had 3x plus 1 over an x squared function, right? So that degree of the top function was less than the degree of the denominator function, so the x-axis was a horizontal asymptote. If the degree of the numerator function equals the degree of the denominator function, then the ratio of the leading coefficients is a horizontal asymptote. So say I've got a function that has f of x equals 3x squared plus or over 2x squared, plus or minus something. Okay, so that means that my horizontal asymptote is going to be the line y equals 3/2. Okay. Next one, if the degree of the numerator function is greater than the degree of the denominator function, then there is no horizontal asymptote. Okay, so say I've got an f of x equals 3x cubed over x. Yeah, top one's bigger than the bottom one, so there is no horizontal asymptote. So let's look at this and figure out the different asymptotes. Here we have numerator function has degree 1, denominator function has degree 2. Since the numerator is less than the denominator, my horizontal asymptote is going to be the line y equals 0, and my vertical is going to happen at my zeros of the denominator function, right? So 2x minus 5 and 3x plus 4 tell me my zeros. So adding 5, I get 2x equals 5. So x equals 5/2 is going to be the line of one of my asymptotes. And subtracting 4, I get 3x equals negative 4. So x equals negative 4/3 is the line of my other horizontal asymptote. So when I'm graphing this out, I've got 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So I've got a horizontal asymptote at the line y equals 0. I've got a vertical asymptote at around 2.5. I've got another vertical asymptote at negative 1.5. Okay? And then I've got some things to do to decide how I'm going to graph this function. Okay? So I want to test some points in this region to see what's happening, in this region to see what's happening, and in this region to see what's happening. Okay, so now let's talk about slant asymptotes. Slant asymptotes happen when the degree of my numerator function is exactly 1 degree higher than the degree of my denominator function. And how we're going to find this is we're going to divide the numerator function by the denominator function. The resulting linear function, not including the remainder, is going to be the equation of my line of my slant asymptote. Now, we know that if we divide a function by another function, if it's 2 degrees higher, well, that would give us like a parabola. 3 degrees higher would give us a cubic. So this 1 degree higher is what really causes that slant asymptote to happen. So let's take a look at what this looks like when we divide the two. So we have 2x squared, okay, and a 0x, right, and a 1. And I'm going to do this with long division just because, I don't know, it seems to be a dying art, and we're dividing by 3x plus 4. We don't really use synthetic division that much with it. It can be done. It's just we haven't really emphasized how to do that. So if we're looking at 3x plus 4, and that's what we're trying to say, is this other thing is being divided by. Excuse me, I'm stammering a bit. So 3x times what is going to be 2x squared? Well, 3x times what gives me 2x squared? Well, that is going to be including an x, but it is also going to have to include a 2 up top and a 3 to cancel that 2 with, right? So this is just going to be 2/3 x, okay? Does everybody see that? Okay, had to do a little equation manipulation off to the side. So 2/3 x times 3x should give me 2x squared. 2/3 x times 4 will give me 8/3 x. And I'll subtract that. And that will give me a negative 8/3 x plus 1. Now 3x times what is negative 8/3 x? Okay, so 3x times what gives me negative 8/3 x. Okay, so I'm going to have to multiply this by negative 8/9, because that way, multiplying that by 3, that'll cancel out, and I'll still have negative 8/3, so minus 8/9. So fraction is getting kind of complicated here, okay? So negative 8/9 times 3 is going to be negative 8/3 x. Negative 8/9 times 4 is going to be negative 32/9. Okay, now at this point, I'm done. I don't care about the remainder. What I needed was this part, okay? Because my line is going to be y equals 2/3 x minus 8/9. And that's the equation of my slant asymptote. I don't even need to do the rest of this math here because I don't care about that remainder. I just needed the linear part here. When we're analyzing graphs of rational functions, it's important to simplify that factor and factor that numerator and denominator functions if you haven't already. Find your y-intercepts, which is f of 0. Find your x-intercepts by finding the zeros of the numerator function, so that when we factor that numerator function, whatever those zeros are, those are our x-intercepts. The zeros of the denominator function are going to be our horizontal asymptotes. And then our vertical asymptotes, we're going to use those vertical asymptote rules and determine if we have any slant asymptotes, because we could have something like that, right? If we don't have vertical asymptotes, we might have slant asymptotes. They don't happen together. Plot at least one point between and one point beyond each x-intercept and vertical asymptote, okay? This will tell you the direction of the function, and then draw your sketch in with some smooth curves. Okay, so here we have some different functions here. Okay, for this first one, we have the line, or the function y equals 1 over x plus 5, okay? And we know by looking at this that the line y equals 0 is going to be a horizontal asymptote because the degree of the numerator is less than the degree of the denominator, okay? We also know that so we have a line y equals 0 is a horizontal asymptote, right? And then the line x equals -5 is a vertical asymptote, right? And we can see that happening with this. And then we could graph points on either side of those to make sure where the direction of our function is, okay? Let's go on to the next function here. And I've already graphed these functions so you can see kind of what they look like. Okay, so we see that the degree of the numerator is the same as the degree of the denominator. Because of that, we can take the ratio of those, and that will be our horizontal asymptote. So the line y equals 3 is a horizontal asymptote. The line x equals -5 is still a vertical asymptote, right? And then we could graph points on either side, okay? We have zeros, x-intercepts at 3x plus 1 equals 0. So x equals -1/3 is going to be an intercept, okay? And we can see that happening right in here with that crossing the x-axis there, okay? So we can see those vertical and horizontal asymptotes happening quite readily there. And of course I would leave it up to you to plot the points yourselves or put them into a table function with your graph. Another function here. Here what we see going on is we have the degree of the numerator is 1 less than the degree of the denominator. So we know that the line y equals 0 is a horizontal asymptote. We see that x equals -5 and x equals 7 are vertical asymptotes, right? We see that x equals -1/3 is our x-intercept. It's happening right around there, okay? And that's from the zeros of that, okay? And then you would plot points to see what this function is doing. We want to make sure this function is doing this and not necessarily doing this or that or something like that, okay? You have to make sure what the direction of the function is doing. Otherwise, you could get very confused and predict incorrectly. So don't just plot one point, plot several points, especially if you're doing this by hand. Okay, here we have the degree of our numerator equals the degree of our denominator, okay? The top function is really x plus 5, x minus 5, right? All over x plus 5, and x minus 7. So, since the degree is equal to each other, we know that the line y, we can look at the coefficients, right? Leading coefficients are all 1, so the line y equals 1 is a horizontal asymptote. Okay, and so now we want to look at our vertical asymptotes. What's happening with this is those cancel each other out, right? And so what we really have here is just x minus 5 divided by x minus 7, okay? Which means that our vertical asymptote is just the line x equals 7. Okay, so don't get confused with this. When these things cancel out, make sure to cancel them out. Okay? And then let's see here. The x-intercept is going to happen at x equals 5, and we see that happening right there. Okay? So that and plotting a few more other points will tell you what your function's doing. So we've learned to find domains of rational functions, how to find horizontal and vertical asymptotes, how to analyze and sketch our graphs of our rational status functions, and how to sketch graphs of rational functions with slant asymptotes. We'll get more practice with this in class as well.